Kepler's laws. The first law, the law of orbits, states all planets move in elliptical orbits, with the Sun at one focus. The second law, the law of areas, states a line that connects a planet to the Sun sweeps out equal areas in equal times. The third law, the law of periods, states the square of a period of any planet is proportional to the cube of a semi-major axis of its orbit. This diagram represents the orbit of some planet. Here you can see the Sun represented by the orange circle, and the gray dot represents a planet moving around it. The two foci of this orbit can be seen in the Sun and its opposing black dot. This simulation will represent some orbit of some planet. One thumbtack represents the Sun, the other represents the other foci. The line drawn represents the path of some planet. In a perfect circle, there will be no distance between the foci. The eccentricity of an orbit is the ratio of the distance between the foci to the major axis of the ellipsis. The eccentricity for a circle is 0. As you can see in this chart, most of the ellipses of the planets are nearly circular, except for Pluto. Kepler's second law states, a line that connects a planet to the Sun sweeps out equal areas in equal times. As you can see in this diagram, the planet is sweeping out equal areas in equal times. Therefore, the planet is moving the fastest as it is closest to the Sun and slowest as it is farthest away. Kepler's third law, the law of periods, states the square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. The semi-major axis is its radius at its largest point of orbit. The period of an orbit is how long a planet takes to complete an entire orbit of the Sun. Therefore, the period squared of some orbit is equal to the cubed major axis multiplied by some constant k. K can be re-expressed by Newton's law of gravitation. Kepler's third law can now be expressed by the period of the planet squared is equal to 4 pi squared divided by the gravitational constant divided by the solar mass multiplied by the major axis cubed, where g is a constant equal to 6.67408 times 10 to the negative 11th.
Now we move on to applications of the Kepler's law. Consider planets' orbit around the Sun. Which of the following comparisons is valid concerning the planet's speed and angular momentum? So at A and B, this is the same planet, and when we talk about angular momentum, we think about the conservation of angular momentum, which states that LA equals to LB. So we eliminate try C, D, and E. And if we break it down, angular momentum of A equals to the radial distance cross the linear momentum at A, and same for object B, which is m times velocity at A equals to RB cross VB. And notice that at both A and B we have the velocity perpendicular to the radial position. So we can write it as RA times VA, m is the same, equals to RB times VB. Now we have, since the radial distance between the Sun and B is obviously larger than A to the Sun, the velocity at A is much bigger than velocity at VB, and we choose A. Two planets of different masses rotate about each other in circular motion. For planet 1, it has a mass of m1 and radius of r1, and similarly, planet 2 has a mass of m2 and radius of r2. For question A, it asks us what is the ratio of the periods of the two planets' orbit. So when we think about the centripetal force that the two planets exerts on each other, they have to be equal in the first place, and their motion should be constantly opposing each other in order to balance out the forces, which means they have the same angular velocity. And the equation for periods, we have the 2 pi over omega, and since their omegas are equal, their periods are also equal to each other. And question B, asks us what is the ratio of the two planets' speeds. So again, we can go back to the T1 equals T2, and the equation for their periods are 2 pi r1 over v1 equals to 2 pi r2 over v2, and then 2 pi goes away, v1 over v2 equals to r1 equals over r2, and this is their ratio. For question C, it asks us to calculate m2 in terms of m1, r1, and r2. So again, we can go back to F centripetal force, and we know that the centripetal force between the two objects are equal, so we can say m1 v1 squared over r1 equals to m2 v2 squared over r2, and from there we can say m2 equals to m1 v1 squared over r1 times r2 v2 squared, and we know the ratio from part B that v1 over v2 equals r1 over r2, so we can rewrite this as m1 r1 squared r2 over r1 r2 squared, and then this cancels out, this also cancels out, so we eventually have m1 r1 over r2, and that is the expression for m2.